Alright, thanks for watching, and today I want to show you a very neat proof that the rank of A transpose equals to the rank of A. And this one is pretty classical, but if you want to see another awesome proof using dual spaces, check out the video I posted in the description and be amazed. But today, just a classical proof, and you need the following facts. So first of all, what is the rank of a linear transformation? The rank of a linear transformation T is just the dimension of the range of T. In other words, if you think of a linear transformation going from V to W, then it takes W to a bunch of outputs. And that's called R of T. In other words, the range, just like the range of a function, is just the set of all possible outputs of T. And this is a vector space and has a dimension, and this sort of the rank measures the size of the output. If the range is three-dimensional, then the rank of T is 3. If it's two-dimensional, then the rank is 2. That's one thing. And also, given a matrix A, we can define a linear transformation LA from, if you want, Rn to Rm. So not LA as in Los Angeles, but LA as in left multiplication by A. And it's defined by LAX equals AX. Simply take a matrix and multiply to the left by A. And I know in your mind sometimes you say stuff like a matrix is 1 to 1, a matrix is onto. Technically it doesn't make sense. A table of numbers cannot be 1 to 1 or onto, but usually the thing you're thinking of is LA, which is the linear transformation associated to A. And before I prove that the rank of A transpose equals to the rank of A, I first want to show that the rank is unaffected by invertible transformations. So claim if P and Q, let's suppose Q is n by n, are invertible, then first of all, the rank of AQ equals to the rank of A. In other words, if you multiply by invertible matrices to the right, it doesn't affect the rank. And why is it true? Just using the definition of the rank of a linear transformation, and I totally forgot to say what's the rank of a matrix. So the rank of A is just the rank of LA. So the linear transformation associated to A, and in particular, what this is, it's the dimension of the range of LA. So one way to show that those two matrices have the same rank, show that LA has the same range as LAQ, which is true here, because what is the range of LAQ? Because by definition of matrix multiplication, left multiplication by AQ is the same thing as left multiplication by Q followed by left multiplication of A. And then, what is the range? It's really the same thing as saying the range of T is the same thing as T of V. It's simply T takes all of V and puts it in this range. So it's really LA of LQ, and Q is n by n, so it's Q of Fn. But here's the thing, Q is invertible, so LQ is onto. Which means it takes all of Fn and maps it to all of the output space, which is also Fn. So that's LA of Fn. But LA of the whole space, that's just the range of LA. So indeed, the range of LAQ equals to the range of LA, and then if you just take the dimension, this by definition will be the rank of AQ, and then this by definition will be the rank of A. So if you multiply A by an invertible matrix to the right, you still get that the ranks are preserved. And same thing if you multiply it by invertible matrix to the left. Okay. And why is that true? Again, let's talk about the range, or I guess now dimension of the range of LPA. That's the dimension of the range of LP composed with LA. And here's one thing you have to understand, or maybe no, soon you have to understand one thing. So that's the dimension of LP of LA of, let's say, Fn. And that's the dimension of, all right, now here's the thing you have to understand. So I'm a bit improvising this, that's what I'm not 100% sure. But if you take a space, let's call this, I don't know, W. And we know that LP is invertible, so in particular it's 1-to-1. Now, here's a fact that you can show, is that if you have a 1-to-1 linear transformation, let's say T, in this case from W to, let's say, W prime, then if T is 1-to-1, the size of the input is equal to the size of the output. That's because T doesn't squish anything. So in particular, if T is 1-to-1, the dimension of TW, equals to the dimension of W. So in particular, the dimension of LP of W, so the image of LP, is equal to the dimension of W, which is equal to the dimension of LAFN. And that's by definition the range of, oh, man, let me restart that. Oh, no. No, sorry. Then, this is the dimension of the range of LA, and that by definition is the rank of A. Or I guess, yeah, then we get that the rank of PA equals to the rank of A. So that's good. And lastly, what do we get? So if we apply invertible matrix to the left, the rank is preserved. And we've shown if we do it on the right, the rank is preserved. So in particular, the rank of PAQ equals to the rank of A. So that was the first ingredient we need. That if you apply invertible linear transformations, the rank is preserved. Now, here's the second ingredient that you need. It's simply, switch lectures. There's this wonderful theorem called what I call the fundamental theorem of rank, which tells you using row and column operations, you can convert any matrix into a particularly nice matrix. So if rank of A equals K, then using row and column operations can transform A into D, which is just of the form an identity matrix of size K and bunch of zeros. So bunch of ones and bunch of zeros. So think of it as like super row reduction. Now, last ingredient that you need, in another video where I talked about elementary matrices, I showed that row operations can be basically written as elementary matrices, and so can column operations. So a matrix way of writing this, it's simply there are invertible matrices, B and C, such that BAC equals to D. So B would correspond to row operations, C would correspond to column operations. And now, oops, that's actually part of the proof of the fundamental theorem of rank, but now we are actually ready to prove that the rank of A transpose equals rank of A. So Clay, rank of A transpose equals rank of A, and you'll see it'll just flow like butter, because what do we know? We know that you can transform A into a matrix D, where D, has a bunch of ones and then just zeros. And the number of ones is just rank of A. Well, in particular, take rank of this. So then the rank of BAC that equals to the rank of D. But B and C are invertible. So by using the third part here, rank of PAC equals rank of A, we get that this equals to the rank of A. So indeed, the rank of D equals to the rank of A. And now, how do we get from this part to A transpose? Just take the transpose of this. So BAC transpose equals D transpose. And by definition of transpose, that's C transpose, A transpose, B transpose equals D transpose. And then take the rank of that. The rank of C transpose, A transpose, B transpose, that equals to the rank of D. But that's also equal because those are invertible. So C transpose inverse is C inverse transpose, which exists. So this is the rank of A transpose. So to show that those two are equal, all we need to show is that the rank of D equals to the rank of D transpose. All right, forgot the transpose, but I kind of think it's obvious. I don't know about you, but for example, if D is 1, 0, 0, 0, 1, 0, then the rank of D, it's simply, and the point is those ones stay where they are, the rank of D, if you want, is a dimension of the column space, for example, and in that case it would be 2. Okay. On the other hand, what is D transpose? That equals to, let's say, 1, 0, 0, 1, 0, 0. And you see the ones are still where they are, and the zeros are still here. So here also the rank of D transpose is also equal to. And so because the rank of D equals to the rank of D transpose, again, if you want to say rigorously, if you want to say this, it's like the first two columns here form a basis for the column space of D, and therefore the ones are in the first two columns. The ones still stay in the first two columns here, and they form a basis for the column space of D transpose. So that works, and that's why, because rank of D equals rank of D transpose, we ultimately get that rank of A equals rank of A transpose, and then we're done. But this is a beautiful computational proof. If you want to see an awesome dual space proof, check out my other video about dual spaces. Alright, I hope you like this math extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.